Hi everyone, I am Sanya Kuller and today we're going to talk about equal density binning and how you can go from how you can get the categorical data from continuous data using equal density binning, where you're trying to make sure that you have an equal number of objects, of items, of numbers inside each bin. So it's one of the ways that we can discretize data. And I'm going to explain to you again. This is called equal frequency binning as well. So let's get started. So just to kind of explain what are continuous and discrete values. So a continuous data value. A set of data is said to be continuous if the values belonging to the set can take on any value within a finite or infinite interval. So it's like something measured, right? It can be anything. You can go like for pi, you can be like 3.14142. And I think at some point you can even find your birthday in pi, or your home number, or all sorts of things you can find when you look into the digits of pi. It's something really cool. So that's continuous because you can slice an interval. You can go down to the decimal place, and decimal places can go on for infinity, right? So if we're like thinking of a height or just something, that's continuous, right? So not exactly countable. So it's like any value. It's measured, like 5.6, 2.489. Like think of temperature, right? Things are like decimal places, and you can keep on going down to the nitty-gritties for the decimal places. So that's continuous. And discrete, I said, no, not that's not what discrete here is, but we're talking about discrete in terms of categories. A set of data is said to be discrete if the values belonging to the set are distinct and separate. So it's counted, it's countable. So you have specific values, you can count them. 1, 2, 3, 4, 5, 6. You can count, for instance, the number of cats. My older sister has a very cute cat called Bandit. And this is just it's so cute just to see this cat, hugging and cuddling, little teddy. It's just so adorable. It just makes my heart melt. So this is just absolutely adorable seeing, this cat. He's reaching out for his teddy, and it's just so adorable. I can't help it. Just so cute. So that's what discrete is. You can count it. And that's what continuous is. It's not exactly countable. You can go down to the decimal places, but for for discrete, you can count it because you can have whole cats. You can count the number of cats. You can count the number of people. Like it's just like you can count something. So just to explain a little bit more, and this is Magic School Bus, one of the shows from my childhood, kind of dating myself. No pun intended, I guess. I love puns as well. But we have these types of quantitative variables, discrete again and continuous. So a discrete variable is characterized by gaps or interruptions in the values that it can assume. Like between one cat and two cats, it's one cat, two cats, three cats, four cats, right? Like it's like we don't have 1.15 cats or 1.156 or 1.3 cats or 1.4 or 2.4 or 2.9 cats. We only have 1, 2, 3, 4 in the number line. But like so if I sketch this number line out here, what we do is we can see, okay, well, along this number line, we have like this is 1, this is here is 2, this is like 3. So discrete is going to be like, for instance, so this is a 3, but the sketches like this is going to be like yellow. Like actually, let me show it this way. Like this is going to be yellow here. This is what discrete is. Discrete is this value here, and also this value here. And this value here. That's what discrete is. Discrete are these values here. That's what a discrete variable is here. So for when we look at discrete, this is what we mean. That's what a discrete variable is. Now for a continuous variable, so again for the discrete, it's going to be this value, or it's going to be this value here too, or it's going to be 1. It's not going to be anything along this interval. That's the difference. For continuous, it can assume any value within a specified relevant interval of values assumed by the variable. Like, so it's going to be able to, for instance, like, for the continuous one, like it could be any of these. It can be any of these values across 1 to 3, for instance. Any of those. That's what a continuous can be. So it can be height, weight, skull circumference. No matter how close together the observed heights of two people, we can find another person whose height falls somewhere in between. So it's almost like, like you could find somebody whose height goes down to the slightest, like, millimeter. That's what, like, in continuous, we can say we can go down to the nitty gritties. We can go down to the smallest, atoms. Like, that's what you can do with continuous variables. And when we're trying to discretize, when we're going essentially from here to here, from continuous all the way to discrete, this is called discretize. So we're going to have some data like gene expression data, for instance, and we're going to want to put it into bins, into numbers. Like we're going to want to have like, bin 1, bin 2, bin 3. This is discrete, bin 3, bin 2, bin 1. We're going to talk in our example about having 4 bins. And this, again, this is the process that I called, it's going to be discretization. That's what this process is. It's going all the way from a continuous value, it could be any value along here, all the way to these discrete, this is a value, this is another value here, this is another value, this is another value, this is another value right here. That is discretization. So we're going all the way here from all these continuous values here, any value here that's all continuous, all the way to these discrete values, where these discrete values are defined by, here and here, sorry, and here and here and here and here, here. Like all these values are discrete. That's the, this is the process that we're calling discretization. And there are 2 main methods that we're going to discuss, and I'm going to cover one in each video. So one is equal width binning. But for equal width binning, each of these bins has the same width, like it's 10 here, 10 here, 10 here, 10 here, 10, 10, 10. This is how like a histogram typically works, So this is 10, 10, 10. This width is the same. Like just almost like a histogram. But for equal depth binning, what you will observe here is that they may not have the same, and going across the y-axis is the number of items inside those bins. So again, this is also the number of items. So what you will observe is that for equal width binning, they may not always have the same number. So this 10, just to remind you, this 10 is basically the interval. That's 10. That's 10. That's the interval. For equal width binning, they all have 10 here for the intervals for this example. And, this is the number of items, the number of values here. That's what this height represents. But for equal depth binning, what we observe here is that all we really care about is having the same number of items inside each bin. It doesn't matter if this one is 22 long, or this one is like 9 long, or this one is 6, or this one is also 6, this one is 4, 7, 7, 8, 18. It doesn't matter. All that, so again, just to clarify, this is this is 22, and this thing here is 9, then this thing here is 6, then this thing here is also 6, this thing here is 18, and this is 7. So it doesn't matter like what the width is here. What they care about in equal depth binning is each bin has the same number of elements. So the difference is each bin has same width. And here, each bin should have like roughly the same width. So it really depends. If it's something odd or something, each bin has same number of items. That's what the thing is, that for equal depth binning, what we're concerned about is that each bin has the same number of items. We don't care about the width of the interval. It could be 22 or 9 or 6 or 6 or 7, for instance, or 18. It can be really long, really wide, really chunky, or it can be small. We just want the same number. We just want bins with the same number of items inside them. But like that's the same number. We're really caring about this height. This is what matters. So what we're caring about here is ultimately, what we're caring about is this. We're caring about, let me show this. We're caring about the height. We want the height to be the same. That's what we care about here. So they should all be the same height. That's what we care about. But for the equal width binning, what we care about is this. We care about the width being the same width. That's what we're caring about, this width. This width. That's the difference. So again, equal width binning cares that each bin has the same width. And again, if it's an odd issue, they should roughly be the same width. And equal depth binning cares that each bin has the same number of items inside it instead. So I'm going to kind of explain more about each of these. So here I kind of want to talk about, feature engineering, deep dive into encoding and binning techniques. So basically, when we're using like machine learning models, for instance, we can do feature engineering, where we can do feature encoding, going from categorical to continuous encoding as well. Like one-hot encoding is very popular for neural networks as well. But pretty much in that kind of encoding, if you have multiple classes, like if you have, classes, like 3 classes, for instance, like in one-hot encoding, what you do is if you have like classes C1, C2, and C3, then the way that you would encode having class 1 would be 1, 0, 0. For class 2, you would say it's 0, 1, 0. And then class 3 would be 0, 0, 1, for instance. So that would be one-hot encoding. So there are multiple different encoding strategies that you can have. And here, what we're going to focus on is like going from continuous data all the way to categorical data through like this feature binning. And we're going to do like equal width binning and then frequency width binning. So equal width binning is also known as uniform binning. And density binning is also known as frequency width binning. So you're sort of, like binning so that you have the same number of objects in each bin. And equal width binning is your binning so that each bin is the same size. And then equal density binning is like equal frequency binning. So you're trying to make sure, and then the garbage bin is trying to say like it's equal density binning. You're trying to make sure that you have roughly the same number of items inside each bin. So each bin has like the same density. That's what's important here. It might be off, give or take, but based on if it's an odd number of things you're putting, if it's not completely divisible. But here we're trying to figure out, okay, well, we have 12 ages. Our x has these 12 ages. So remember, this is our x here. Our x is here. This is our x, a random variable. It's got these values here. We're trying to discretize it into these bins. So yeah, so then this would be, these parts here would be all in like value 1. These would be value 2. And you notice the same number of elements would be in each one. This would be 3. And then this one here would be 4. So roughly, like, they have the same number of items because it works out to 12 12 is a number of items here, 12 divided by x, now we want 4 bins, number of categories, and this is giant x. X is this whole random variable of the ages. So this n here is going to be 12 items because there are 12 ages. And x is going to be 4 because we want 4 bins. So the frequency means we want to have 3 items in each bin. That's how this works. So that's like this frequency of 3. That's why we have 3 items here, 3 items, 3 items, 3 items. And then we can kind of compare them, like this is Python code kind of using this age. If you have that age variable, this sort of shows you how equal frequency binning works and how equal width binning works. So it's sort of the opposite idea that equal width binning, you may not always have the same density in each bin, but each bin is going to have the same width along. It's just like the same marks. You might not have the same, like it's the same way of binning information and kind of putting continuous data into groups or categories, for work. So equal width, they just have the same width, but we may not have the same number of items inside each bin. But equal frequency, on the other hand, is saying that each bin has the same number of items. I mean, it's really trying to, if it can be divisible properly, it is supposed to typically have the same exact number of items inside it, but the widths of these intervals might not always be the same. As long as each one has, you just sequentially put each one in the bin, the next one in a bin, the next one in a bin, the next one in a bin, so that you have the same number of items. And this one is just like, okay, we have the bin max, we have the regions, we're just going to assign whatever comes in this region, like there, it just, everything has equal width. And it's just Python code as well. Like if you want to kind of look at the comparisons of, these are two of the main binning strategies we're going to talk about today. But instead, we could also just look, instead of the different stages, for instance, just pretend we're looking at different time points for 5 genes. So this is an example we're going to try to work through. Like how will we find the mutual information and calculate it between these genes? So we want to calculate the mutual information between all pairs of genes. And then, so here we're just going to pretend like we really don't know who's the transcription factor, and we're just like which ones aren't. So we're just going to calculate the mutual information between gene 1 and gene 2. Gene 1 and gene 3, gene 1 and gene 4, gene 1 and gene 5, for instance. Then we want to calculate that information between gene 2 and gene 3, because remember that we already have it between gene 1 and gene 2. Then gene 2 and gene 4, gene 2 and gene 5. And then we also need to calculate the mutual information between gene 3 and gene 4 and gene 3 and gene 5. And lastly, we need to calculate it between gene 4 and gene 5. So the way that we can do that is by sort of looking within this given gene, and we can sort of do some binning first and say, okay, well, let's look at the expression of these different genes. Let's see how they are in terms of their expression levels throughout, these time points from 0 to 150. We can look at time points maybe for the same individual at different time points. Maybe like this guy, we can focus on his Alzheimer's disease progression. And I know these timings do not make sense, but then we're looking at 5 genes. We're basically looking at all the genes, but we're just focusing on a small toy example here, where we typically, this data would actually look much inverted, where it would look like kind of like the opposite of how it looks. So I really hope that instead you can see that it would look just like this, like a rectangle with way more genes than samples or time points. But we're just trying to show here that we have these time points, and we're going to try to analyze based on these time points and the behavior, what is the information, like, like maybe at a certain time point, as this guy's getting older, we would notice maybe that there is some neurodegeneration or some phenomenon is happening, as we're going down in terms of the time. So we're trying to basically figure out how can we group these genes. And that's how mutual information comes in. So we're going to figure out first within each gene, how can we bin it in terms of its expression levels? Like, in terms of the minimum or the maximum values, like we should assign these values to given bins based on the distribution of each gene. Because each gene has its own distribution, and we want to use that information when calculating the mutual information. So we're going to discuss the 2 different binning strategies that we could use. And for all of these 5 different genes, for these 16 different time points in this example, we can sort of see what the typical gene expression levels are. So this is frequency, but what this really are, the y-axis, this is just mainly measuring like the gene expression values and frequency. So these are histograms. So this is known as a histogram. Each of these is a histogram. So what these histograms do is they come up with their way of sort of binning these observations into different
into different bins over here. Like, so they're coming up with their own binning strategies based on their binning. And, you know, we can see gene 1's expression values, gene 2's expression values are here, gene 3's expression values, gene 4's expression values, and gene 5's expression values. So right off the bat, what you can see is that these go up to like 1, 1, and 1. So these are like, so these three, I'll just have like a little, maybe I'll use this color. These three have pretty high expression values going up to 1, whereas gene 1 and gene 5, their expressions, like this one goes to 0.5 and this one does 0.25, so they're like have relatively lower expression usually. So if we want to compare how gene 1's expression is changing, it's pretty low in general for gene 1 and for gene 3. So if we want to see how these expressions are changing during the 16 time points, it won't make sense to just compare, okay, well, gene 1 is this value and gene 3, gene 4. It doesn't make sense, right? Like if you have somebody that you know who's really skilled, like let's say your parents or guardians are really good cooks, right? And you may or may not be, you know? Please don't take offense, but like let's say that somebody who's been cooking a lot longer, right? For instance, is really good at cooking. So if that person is learning a new recipe versus you, that person is going to probably make it like a lot better than you could, because they're already going to be super skilled at it. Like one of the things I love doing is I love to knit actually. So this is my yarn here. So I'm trying to make something as well. But if somebody who doesn't know like as much like knitting, or who doesn't know as much of you know, like let's say you don't know enough cooking or somebody else knows it, the idea is that they're going to pick up like a lot faster than you in the same amount of time. The person who's skilled is going to pick up a lot faster than the person who's not skilled. So somebody who's learning how to cook a new recipe versus somebody who's skilled at cooking, learning a new recipe, the person who's skilled is going to learn it faster, right? So it doesn't sometimes make sense to compare these values of gene expression, especially when they're on different scales, right? Like if we had to say, oh man, like how come you didn't learn this recipe and this other person who's super skilled learned it better than you, or they made the dish way better? No, it doesn't make sense that way. It makes sense to say, okay, where did you come from? You're not as skilled at cooking. Sorry, again, please don't take offense. This is just an example. You're not as skilled at it, right? Or well, like for me, for knitting, this is my grandma. She is super, my paternal grandma, she is super skilled at knitting, and she can knit something that would take me like weeks and weeks. She can probably knit it in a couple of days because she's super, super fast, you know, at knitting. In general, she makes very beautiful sweaters as well. Like she's super skilled. And pretty much the idea is that something that would take her a much shorter amount of time would take me a longer amount of time. So everything is all relative. So the key idea is that we want to make sure we're looking at like on a typical level. You know, like if this amount of time takes me this much time to make the same material when I'm knitting, or if I'm cooking, or if I'm doing something, it might take somebody who's more skilled less time to cook, or it might take them, like my grandma, less time to do the knitting. So we shouldn't be comparing the quantities per se or the quality per se, but we should be looking at like the changes in general. Like, are we noticing that like I'm doing better? So my idea is that we're not looking at the absolute quantities for these. We're trying to find ways to bin these values and then compare them, because gene 1's expression is never going to be higher than gene 3. Never going to reach gene 3's level of 1. It's never going to reach gene 4's level of 1 either. or gene 2's expression of 1, for instance, or even gene 5's expression of 0.5 here. That's just not like how its value varies. But we should see over time, are we observing the same trends over these 16 time points? That means like when gene 1's values is going up relative to its other values, are we noticing the same behavior for gene 3 or gene 4 or gene 5 or gene 2, such that knowing something about gene 1's expression can tell us something about the expression of the other genes? That's what mutual information is telling us. Like in sequence logos, does knowing something about like a position along the motif, do we know more that that base is likely to be a given base or not? Like basically, how much information do we have? And if we know that gene 1 and gene 3 tend to move in similar directions, right? Maybe at a certain time point, they really spike and then they go down. Maybe the cyclical behavior where they shoot up and then go down, shoot up and then go, shoot up and then go down, shoot up and then go down. Maybe it's cyclical, or maybe it's just increasing together. Maybe it's all decreasing. So it's like we want to compare how it's moving relative, right? So I can't compare myself with the experts in the world who are great at knitting or who are great at cooking, you know, great at video games or great at sketching, you know. Like if I made a star that looks just like this, I should be happy. Somebody else could draw a very beautiful star, right? But I'm getting better, which is nice, right? So the key idea is we want to bin these things into bins, like maybe using equal width, equal density, and we're binning it based on each gene's own values. And we're binning it based on its own values, and based on its own values, and based on its own values, respective values, and its own values. And we're seeing how does its behavior across the 16 time points, how does that behavior change? And are there similarities in the changes between these genes and, you know, these genes and these genes and these genes? So we're basically taking all pairwise, and then these genes, and then these genes, and then these genes, and then like this and this and this and this and this. You know, like hopefully try to capture as many pairwise as possible. But we'll be basically looking at, you know, 1, 2. comparison of those genes. Then we'll be comparing 1, 3, then 1, 4, like those genes, and then 1, 5, and 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and last but not least 4, 5. And what this is this is basically like this is a gene I. I can just write maybe gene A and then gene B. And we're just looking at all these combinations, and we're just trying to figure out, like, you know, that's what we're trying to do. And again, these are like the expression values, and our goal is to bin them. You want to put these into proper bins so that we can try to see how are they changing together based on their relative values. You know, we want to bin them based on their relative values using either equal width or equal density binning. Those are two main strategies to bin them based on their relative expressions. Put them into bins. That's our goal.
So basically, now we have two different strategies that we can use to bin the values for each gene. So we're going to focus on each gene. For instance, like we have these 5 genes, and we're going to look at gene 1 in this example. And then we're going to look at gene 2, 3, and 4, and 5. And for each of these genes, we're going to look at all of its values for whatever it is. It could be a set of individuals in different stages of Alzheimer's, for instance, or a bunch of different time points, or anything. It's just, all that matters is that this thing is just either it's like different people, and we just want to find that the changes in these expressions along for these should be the same. They should follow the same patterns in general, because maybe this gene has a high expression level than this gene, for instance. So it just makes sense to say that relative to this expression, how is it changing in terms of its binning as we go throughout the time points? That's what we're interested in seeing. How does this change in its overall expression, looking at its minimum to its maximum, and like we're putting it in bins, how does this behavior change during time, or during, as we are progressing from patients who have no Alzheimer's to those who have Alzheimer's that's very severe. So like these conditions as we're going down, these represent the similar conditions for these people. For these time points, and for these different genes, and we're trying to see if the behavior changes are the same, and then there could be some mechanism of transcription that could be taking place. But basically we're trying to calculate the mutual information, because if their behavior is going in a similar direction, where maybe these maximum, this is like maybe this is the maximum values are here. But it doesn't seem like here, it seems like this maximum value and this maximum, these are higher values, they're not quite moving in the same direction, for instance, there. So we would be saying, okay, like, so the one way to say is that, okay, this way we could look at it is we could look at the minimum values or the maximum values, and we could say, okay, well, it seems like 0.24, like these values seem like they're the higher ones. For instance, like these seem like the higher ones for this gene. And then for the other gene, maybe like what we see is like 0.92 is really high. It's got really high values. Is there any like kind of connection between these? Is there any kind of connection? Maybe I'll also just, for similarity, I'll also just, highlight like 0.83, even though it's a little bit off. There's a little bit more of a greater difference. So we can look at gene 2 and see, well, these maximums don't quite be, tend to move in the same direction, right? So like the expression levels are on very different altogether, different levels. Maybe it's just the way that gene is. So we want a fairer metric of comparison to say that, okay, out of all these expression levels for this gene, how is its behavior changing? Then for all of the expressions for this gene, how is its behavior changing during these time points? And then for this gene, how is its behavior changing, like the maximums and all of that? Like, how is it changing? And do they tend to change in similar ways? So that's what binning is going to tell us. For each column, we're going to put these maybe into like we're going to put these in probably like a maximum bin. For instance, like a maximum bin could put these in one bin together. And then it could put other values like the second tier in another set of bins, and then the third tier, and then we'll have one for the smallest one. That's what we're doing here. We're binning along each column. And there are two different ways for us to do this binning. One is equal width binning, where the bins will have the same width along, like maybe we want like, we look here and we divide it into equal set of bins, with the width are the same. Maybe we take the min minus the maximum, and then we find the number of bins we want, and each bin will have the same width. And that could be a strategy that we just focus on, like, they have the same width, and, this is another bin with the same exact width, for instance. Actually, it doesn't quite look good, but the general idea is we could look at equal width binning or equal density binning. Equal density is saying that each bin should have the same number of genes in it. Like maybe we'll have the top 4, the next top 4, then the next top 4, then the smallest top 4, for instance. Oh, sorry, it would be like the top 4, then the second 4, then the third 4, for instance, and then maybe the bottom 4, like the minimum 4, for instance, like the lowest. There could be multiple ways to bin this data for each gene. It just matters that we do it in a consistent way. So we can either use equal width binning or equal density binning. And the important thing is that we figure out what is the optimal number of bins that we want to use, and what strategy do we want to try out. So now we're going to talk about equal density binning, or also known as equal frequency binning, and we're going to walk through an example of how we would do that for these 5 different genes that we are interested in at these different time points. Remember, instead of time points, it could be something else as well. So let's get started.
So you can sort of think of equal density binning, like for now we're focusing on gene 1 and we're binning it. So you can think of equal density as sort of trying to find the bin strategy that we would have each bin with the same number of elements inside it. So for instance, in bin 1, we want to have four genes inside it. 4 gene time points inside it, like so for 4 different time points. So this is the expression of gene 1 across these different time points. So in each bin, we want to have the same number of time points as much as possible. I mean, if you have odd numbers or some things don't work out, then we might have to make adjustments. But think of it like a traffic signal where, you know, there's like a police car and he's saying, oh, he or she's saying, we want only 4 people to go each time. Dun, 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 dun. Okay, done. Because we have 16 time points, so if we have 4 bins, we will have 4, 4, 4, 4. Of course, if this is odd, if it doesn't, you know, exactly work out, like if we have these 16 time points but we want 5 bins, then, you know, it's not exactly going to be equal number of items in each bin. And that will really depend then on your implementation of mutual information, the binning strategy for equal density. But we want each bin to have the same number of elements inside it. So that's the goal of equal density binning. So in short, in equal density binning, usually has the same number of elements. That's the goal of equal density binning. So here we have 4 elements here, we have 4 elements here, we've got 4 elements here, and we've got 4 elements here, and we sort the gene 1 values from least to greatest. So that's what we're doing over here, and we can see that I just sorted it from the minimum value all the way down to the maximum value here, and the time points are all shuffled around based on that. So I first sorted them and I said, okay, these are all like the first 4, so this belongs to one bin. The next 4 belong to the other bin. These next 4 belong to bin 3. And these last 4 belong to bin 4. And again, based on the other situations, it might vary. So, so in my situation in particular, my implementation, this is how I've done it based on, like, let's say I want, like, so what, right now we were looking at 4 bins. So what we were just talking about was this situation here. This situation. We were just talking about 4 bins. Yeah, maybe I'll just leave for a second so you have this. So this is like what we were looking at right now. Is equal density binning results for gene 1 for different number of bins. So if we have 2 bins, 3, 4, 5, 6, 7, 8, and 9 bins. And again, right now, I had just shown how we would calculate it for 4 bins, you know, making sure we have like the 4 here, 4 here, 4 here, and 4 here in each of these. So the thing that I did is I just sorted it from the smallest value, so this is the minimum, to the min, all the way to our maximum value. So you just have to sort it, you know, that's what this is saying, sorted it from least to greatest. So least to greatest here, least to greatest. The minimum refers to these values here. Minimum, and this is the maximum value here. And then you just bin accordingly. So what this is saying is 2 bins, so you roughly have 8. 1, 2, 3, 4, 5, 6, 7, 8. So you can see 8 here. And then the last 8 here for 2 bins. So you're making sure you have, you know, this is bin 1, this is bin 2. And then for 3, it sort of differed because of my implementation. So so just try, these are edge cases, maybe don't focus as much on them. But you've got 1, it has 3 items in it. 2, bin 1 has these 3 smallest. Then bin 2 has the next 3. Then bin 3 has the next 3. Bin 4 has the next 3, and bin 5 has the top 4. You know, so that's how it was partitioned. And then you can see how they kind of change a bit for 6 bins. You know, so this is sort of overall, like the overall values are like this has 3 elements in it. 3, 2, 2, 3, and 3. And again, this had like the way that this was split was this is 3, 3, 3, 3, and 4, 8, 8. This is like four items here. You know, you sort them from least to greatest. Now later on we're going to like sort it back and then see where they all fall. And again, this is just for gene 1, so you'll have to do this. This is for equal density. You'll have to do this for the other methods too. So now we see here, this is 3, 2, 2, 2, 2, 2, 3. This is 2 here, 2, 2, items 2, 2, 2, and 2. So I'm just counting the number of items in each bin. Again, this is a little, not the greatest implementation idea for 3 bins, so I just don't want to worry too much about that. But pretty much, either this is 2, and 2, this happened to be 1, 2, 2, 1. It also again depends 2, 2, and 2. So the reason you'll see this is because we have 16 items, 16. So again, we have 16 time points. What's the clock? 16 time points. And if we try to have like 9 bins, which is what this is, we're not gonna have 16 over 9. You know, we're kind of short 2, so a couple of bins will take the hit. Like this bin over here, bin 3 and bin 6 are going to have only 1 item inside them because you have 16 and you have 9 bins and you have 16 time points, so 16 total elements here, so you're not gonna have enough for 2 in each. So this was exactly 2, but then now you have more bins. So now you're gonna have like less, and then 16 bins, you have each one is its own time point. Each bin corresponds to its own time point over here and its own expression value. So that's sort of what I would say, like for rounding purposes as well. Maybe just keep all the decimal places and and then sort them based on all these decimal places, then round them afterwards. So that's sort of like how for equal density binning you take the minimum to the maximum. That's how this is looking overall. You're going from minimum all the way down to maximum and you're sorting it. That's what the sorting is. Sorting it from min to max. For all these bins, I just kept the sorting the same, and I just sort of made sure that based on I want to have 3 bins, so I'm going to sort them so that I have 3 bins, 1 to 3. I want 2 bins, so I have 1 and 2. I want 4 bins here, 1, 2, 3, and 4 are my bins. 5 bins, 1, 2, 3, 4, 5. These are the bins that they are assigned to. 6 bins, it goes all the way from 1 to 6. 7 bins, the bin numbers are going all the way from 1 to 7. 8 bins, 1 all the way to 8. 9 bins, 1 all the way to 9. So that's how you do equal density binning here. And then what I'm going to do is I'm just going to now sort them time values least to greatest. So now instead you'll see here that it's just going from 0 all the way to 150. That's what we're doing here. We're just sort of sorting them by time. Just a progression of time. And we're sorting these values, and what you'll see now, like this is 1, 1, 1, 2, 1, 1. So this is just going to be how I'm going to like have this show up for these different number of bins. But in reality, we're just going to choose a number, so you can just see how the bins and the assignments of gene value differs. So we can think of the initial histogram and how that changes based on like where will the cutoffs be based on how many bins I want. So pretty much just to clarify again is that you can see that this is gene 1 expression and we're focusing on gene 1 and we'll do the same process for all the other genes. And we just sort of see that based on the number of bins here, like here 1, 2, 3, 4, 5, and the histograms are using their own binning strategy. But based on the number of bins that we want, the data points will be assigned to their own respective bins. Like the way to see this is that this is our bin 1, 2, 5, and this is like how usually how equal width binning is done, because these are all like the equal width, and you can see that the density, the frequency is different. So this is not equal density, this is like equal width. So this is like 0.05, 0.05, 0.05, 0.05, 0.05, but so that's what we would get to with equal width next. But I just want you to see the idea that based on the number of bins that we have, so as we add or change this, we would get like very different results, you know. And typically like normal distributions look like and that is usually the result of like, you know, we are taking all of these values from the histogram and that's typically, sorry for the bad sketch, but that's usually how a normal distribution looks. But in general, like based on the data, like this is just showing based on the number of bins that we want, how do these original data points for gene 1, how would they get sorted into the different bins, you know, and that's what these are. Like this again would be like, this would be bin 5, bin, and this would be like another, the other bin. So based on that, we'll be focused on 4 bins over here. So that it means that we're just going to focus on this value right here, 4 bins. So we're going to take these values here and we're just going to work with these for now. So we're just going to work with these values. Four bins for gene 1. And I just wanted you to sort of see kind of what happens if we were to change these a bit.
So here, like, let's say that we're now looking at 4 bins, equal density binning. So for each of them, again, for each of these genes, we're going to do separate binning. So we're going to put them in each of their respective bins. And here, let's go ahead with 4 bins and assume that we're trying to put each of these genes you know, into bins 1, 2, 3, or 4 at each of these time points. So now we're going to look at gene 2 and focus on equal density binning for 4 bins. And I was showing before how we can vary the bins and how we can get different results based on that. So what we're going to do is we're going to sort the time points by gene expression value. So we have these 16 total time points here, and that corresponds to 4 different bins. So please assign the sorted values into the B bin such that each bin contains the same number of elements. So in equal density binning, we want them to have the same number of elements in each bin. That's the goal. So let's focus on gene 2 again, you know, with 4 bins. So the way, so this is like, you know, the Cars show, Lightning McQueen, you know, the Cars movie, you know, like it was a great movie. It is a great movie. So let's pretend. So the way I think about it is like, imagine you're trying to go on a roller coaster. I'm so scared of heights, so I probably don't want to go with that analogy. But like, you know, you have to, you know, it's a queue. You have to wait every few people is allowed in on the roller coaster. You know, every few people like is allowed. The roller coaster has so much capacity. So similarly, you know, the number of people in line, you know, you have to go based on that. But how do we do it for equal density binning? Well, to figure out, you know, which people get to go at each time, or which bins each of these gene expression is at a certain time point. And remember, time can be one of the factors that we can do these binning on. It really depends on the nature of the data. It can be time values, it can be different stages, like I was showing you Alzheimer's stages, for instance. So what you do is you have this for each gene. So now we're focused on gene 2. So we're going to sort it from least to greatest gene expression value. So you can see here this 30, you know, yellow is 0.21, no, 0.129, and the maximum value is over here. So you can see this whole spread. So we're going to focus on equal density binning for gene 2. So now we're over here. And now we're going to see, okay, well, let's focus on this first car. And this first car is going to be bin 1, which is level 1. So it's allowed to go. Then we focus on the second car over here. And that's, 0.1502. So this is the second value in line. And it's still allowed to go. So the first value is here, and the second one is also on this level. So each parking level will have a capacity of 4 cars. So next we also see that, car 3 is going 0.164307309. This is the third value over here. And it's also going to make it onto bin 1. So, the traffic light is saying, okay, it's green, you can keep going. Imagine the traffic signal is allowing just every 4 cars to go in, on one parking level. So we have the first 2 over here, they've made it onto the same level, and this one is also going to be able to pass onto level 1. And then we have our last one here. And so now this value is also going to be, this car, this fourth value here is also going to be able to just make the cut and make it on the level. So now we have 4, we're at capacity now. So now this next car is going to come. It's going to be really disappointed. It's going to say, huh? You don't have a spot for me? Okay, well, there's no more room on this level. Oh gosh, it's not letting me through. So I led the first 4, and then it's like, no more allowed. It's like, oh man, now I have to wait for the next level to open up. Now I have to go on the next level. So problem solved. There's another level that's open. So this car is going to go right on to the level 2, the next bin number 2. And also just a friendly reminder is that, remember these values over here, they've already kind of been assigned to our bin 1 here. So now we are, have 2, this is going to be our second value on level 2, a second car, 0.0417, it's going to be here on the second level over here, and then similarly the third car is going to be able to enter in as well, which is 0.57, so it's also going to be allowed. And this last 1.60288 is just going to make the cut. We have 3 cars here. We can only have 4 on each level. So remember, because we had 16 values and 16 time points and 4 bins, so that was 16 over 4, which is 4 is the bin size. That's the bin size. That's the capacity that we have. So these 4 are going to be, all these 4 cars have made it into our bin 2. So these 4 have just finished making our bin 2. So now no other cars are going to come. So now when we go on to the next one at a time point 110, 0.608, and then remember what we care about is the sorting of these expression values here. So now this guy's going to come and he's going to be like, oh, there's no more space for me. No, you can't go. These other 4 are occupied. You got to go on the next level. Sorry. So this guy's going to have to go on the next level now. The stop, so every 4 are allowed, and then the stop sign comes and you can't go. So now the level has changed to the level 3. So now this one is going to be the start of bin 3. So it's now allowed to go on to bin 3. Similarly, now we also have this next car, which is 0.622, and it's going to also be allowed on the level. There's 1 car over here from the same bin 3 already over there, so we can allow the next car. And the next car is also going to go to bin 3, level 3 of the parking lot. And then 0.79 is also going to make it. The 3 other cars, so this guy's just going to make the cut. And then, as you can predict, then the last next car comes, this 0.825 is going to say, nope, you're not allowed. We have 4 already. End of this bin, end of this parking lot. We have to have a new level. So, so pretty much just to sum up, what we already have is that we saw that these 4 have already made it. This would be our bin 3. These first 3 here were our bin 1. The first 4 were bin 1. Then these ones have made it to our bin 2. 40, this one. Yeah, these ones were our bin 2. Bin 2. And then now we are finished our bin 3. So now this car has to wait and go on to bin 4. So you can see we're at the last bin. So we were supposed to have bins 1, 2, 3, and 4. So these next 4 cars are going to make it on the last level, and then we're done. So all of these get assigned to bin 4. These last 4 cars make it onto bin 4. And you can see that this is the maximum value car over here. So I hope that this analogy helped, sort of how we sort, not by time, but by the gene expression value. And then the first 4 make it into one bin. They make it into one bin. Then these next ones make it into the next bin. Then these ones make it into the next bin. And then lastly, we have like this bin here. And sorry, this orange one should be including this. So that's how we can get our bins. We bin them based by our gene expression value, so that each of these levels has only 4 cars, because it happens to be because 16 divided by 4 bins is 4. But that's what, like, the bin size will depend on the number of points and the number of bins that you want. So if we only want 2 bins, we would have, like, these would be 1 bin, 8 values, and then these other 8 would be the second bin. So that's how we do equal density binning. So each level has the same number of elements, same number of cars inside it. And it doesn't matter what the intervals are, they each have the same number of elements inside them. So again, hopefully this should kind of highlight how you can go from a gene, like gene 2, and you sort it based on its expression values from least to greatest. So least value all the way to minimum to maximum. Again, so that's, min all the way to maximum gene expression value. Typically write in cursive, but so this is the minimum value. It's not as clean if I write it online, but it's all good though. So we typically sort the value from minimum to maximum. We bin it, these first 4, we just have like a divider that's going across like every 4, in a way, just saying, okay, every 4 have made 1 here, just divided by every 4, then the next 4, then the next 4, like it's all based on your bin sizing. So it's not like as neat. But then after you finish sorting them out like this way, then it's just like you sort again on the time. You sort it here on this column on the expression value, but now you're just going to sort on the time again, and this will be like what values you get for gene 2 here using equal density binning. You can see like these are back to back, so it goes from its maximum value at time 20 all the way down to its minimum value across these 16 time points, right back to back. So you don't jump from 4 to 1. So similarly, we can do the same thing for each column separately. So again, we have to take each all the gene expression values, please sort from least to greatest gene expression value here. So what we're going here is we see that this is the maximum value here, and this also happens to be the minimum. So similar to gene 2, they're like back to back. But now we sort it not on time, but on the gene expression value here. And then what we see is that we can do equal density binning. And then after we do equal density binning, we can then get 1, 2, 3, and 4. We just divided where the bottom 4 are, the 4 highest values are in bin 4. Then the next 4 make it into bin 3. Then the next ones make it into bin 2. Then the next ones make it into bin 1. The smallest 4 are in bin 1. From least to greatest. So think of it like, every 4 make it onto a parking level. You're part of it, part of it, part of it. And as soon as you're not part of this level. So it's like, you can think of it again like this. For this bin 1, you can think of, okay, well, you're allowed. Okay, so you're allowed. Okay, that's it. You're not allowed over here. A new parking thing is in order. These 4 are in 1. These next ones make it into 1, and then these last 4 make it into the other parking level. So that's how we do the binning. And it helps to sort them from least to greatest value, and then bin them, and then in the end you just sort again by time. So that's like a really quick strategy. And you can do the same thing for gene 4, where we see these values are sorted originally by time, from time 0 to 150. Then we sort by minimum to maximum gene expression value. Then we place 4 in each bin sequentially. These 4 make it into 1 bin, then these next 4 expression values make it. Then the next 4 make it into bin 3, and the 4 highest make it into bin 4. And then so we sorted it on expression value to get it, and then we restored the original sorting, which was by on time. And this shows like how we have gotten the bins for each time point using the distribution of this gene 4 as well, using the condition that the same number of genes, gene time points should be in each bin, same number of cars on each parking lot, same number of people are allowed on the roller coaster ride. And of course, they might be off based on like, if you have an odd number or, if it's not completely divisible. Here, it just turned out we have 4 bins and, 16 time points or 4 bins with 4 elements each. So that worked out, but it may not always be the case. But for the most part, it depends on the algorithm you're implementing. So here, again, you're sorting it and, you're putting it again for gene 5, we resorting it. And that also goes to show you that we sort each gene column for its expression values. And then, then we bin them again, each 4, the next 4 in the next bin, next 4 in the next bin, and the top 4 are in this last bin 4. And we had sorted it on expression, and this is us, sorting it again on time, restoring the balance. Happy clock. So, restoring it, and these are like how the bins go from time 0 to 150. So we've gotten our equal density binning. So we'll have like the 4, like these 4 ones are like scattered here, 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 as well down there. So this shows the equal density binning. So this is sort of an overview, and you can see that the behavior changes, for equal density binning from gene 1, 2, 3, 4, 5, as we go along for each of these different bins. Each of these different genes, like their, as I mentioned, their expression levels are different. Like this is, going from, 0.004 all the way to 0.249. This one's going from 0.212 to 0.93. So it's even much higher, the comparison between these two, the values, it's like this is almost, this is like much smaller. Much smaller range, like this is like really small, and the range of values is different. So we really can only, some genes, for instance, in the cell always need to be produced at a higher level. Maybe they're housekeeping genes, maybe they're doing some things that are really important in the cell, so they'll always be at a higher level than some of these genes. Or maybe they're also specific to the tissue or the cell type, So that's why we really have to go on how these bins have changed. These bins are based on the distribution for that given gene. So we have to go on how do these bin values change? How do the distribution of gene values in these bins, how is it changing? That's what we're looking at. So we're looking within each, that's why we're doing the binning for each gene separately. We're sort of seeing how does gene 1's expression values, how do those change for each of these time points relative to what other expression values it's had? That's what bins 1, 2, 3, and 4 tell us. And over here, we're also doing the similar binning where we're also looking and seeing, okay, well, how does that change for gene 2 across its values from 0.12 to 0.939? Like we defined our bins, making sure that there are 4 in each bin. How does that change? What about for gene 3? What we see here is that like at time point 0, for instance, then, genes 2, 3, 4 are in the smallest values. Then gene 1 and 5 actually on the second value, like second bin, like with respect to what they typically are. So like we can see here that at time point 50, if we're comparing across, well, it looks like gene 2 is in one of its highest values that it's been, like it's in bin 4. But, and these other ones are in 2 as well, and this one's also like in 3. But for gene 5, it's one of the lowest values that it's had. Its lowest value is here at 1. It's in bin 1. But for the gene 2, it's actually in bin 4. So it's one of its highest values at this time point. So we're sort of comparing not these values with each other, but the binning, the changing in the distributions of the gene, of that gene's expression values across the time points. We're sort of seeing the comparisons between gene 1 and the gene 2's changing relative to its other values, and gene 3 changing relative to its other values, and gene 4 changing relative to its other values, and gene 5 changing relative to its other values. So it's all relative to its other values. That's how what binning tells us. But this is equal density binning. The results would change for, for like equal width binning. So these are ensuring we have 4 in each of these bins. You can see like how the behavior is somewhat different. Like we can see maybe like genes 3 and 4 are a little bit more similar, you know, like they are at 80, they're at their minimum, and then at 100, they're at their maximum. So maybe there's something going on. Maybe they're like buddies, you know, that may be moving more together, but we have to analyze more things as well. We already see that there are quite a few overlaps as well, where we tend to observe like this 2, 3, 2. They seem to be like similar, like a little bit similar, but not quite, like 1, 4, 4, 1, 4, 4. You know, they have that, you know, initial like, you know, behavior going on as well. So we have to keep our eyes peeled. You know, you gotta keep our eye out. You know, do we really observe that? And this is equal density binning results again, you know, for these 5 genes. You know, these are the values, minimum, maximum. You know, minimum is in yellow, maximum is in orange. And this is just a sort of a summary back to back to back, how we can see their behavior, you know, changing across the time points for equal density binning. So each bin has the same number of values. You know, but if it's not exactly like, you know, divisible, they should have approximately the same number, you know, give or take a couple, you know. So usually the same number of elements in each bin. So that's how you would do that. Thank you so much for watching my video. If you like it, please subscribe to my channel, and be sure to like it if you really like thought this was useful. So just signing off with my favorite logo, the smiley. So yeah, just thank you guys for watching. And again, I'm Sonia Cutter, and I'm really happy to help you know, teaching and explaining certain concepts. So please reach out to me if you have any questions at all, and I'll be happy to help. So thank you for learning about binning and discretization with me today. Thank you guys.